Hello everyone, I'm very happy to give this talk on my result, classical verification of quantum computation in linear time. I'm Jiayu from Caltech, and this talk is based on my recent paper, whose newest version is on ePrint. This talk will be divided into 3 parts: background, results, and techniques. Let's first review the background. So what is verification of quantum computations? Suppose you have a quantum circuit C and want to evaluate and get C0, but it doesn't have the ability to apply C itself. So you make use of a remote quantum server, which might be a service provided by IBM or Google, and they run it for you and told you the result of C0 is 5, for example, and you don't want to trust them. Should I believe them? Maybe these commercial companies are just outputting random numbers and pretend they have quantum computer capacities. And possibly, the result of this circuit is so important for you that you can't wait until real-life experiments or real-life applications to see whether it works or not. Possibly, you need to use it to design molecules, to design medicines, which might lead to real-life disasters if the computation result is wrong. So you need such a protocol that you can interact with the server to verify the result, such that if the server is trying to cheat, you will either detect it or verify the result. This problem is very fundamental in quantum computation and cryptography. And as we discussed just now, it has very strong practical motivations. And theoretically, the study of these problems has often led to surprising results in both complexity theory and cryptography. And ideally, we want this protocol to be a classical client protocol, which is a classical verification of quantum computation problem. Practically, we want such a protocol because a user might not have a personal quantum computer. So what it can do is just classical computation and classical interactions with the server. And this problem turns out to be very tricky because in our setting, the client only has limited or even no quantum computer. How could such a client verify arbitrary quantum computations? What's more, quantum computation behave very differently from classical computations. For example, in quantum world, intermediate measurements could destroy computations. So the client could not ask the server to provide a transcript of computations or similar things. So what we can do, before we discuss our solution, let's first formalize this problem. The minimum requirement for this problem is completeness and soundness requirement. For completeness or correctness, it means if the proposed output is correct, and if the server is honest, which means it follows the protocol, it will make the client accept. And soundness means if the proposed output is wrong, which means the server is trying to cheat, then no server could make the client accept. So the cheating will be detected. And in formal definition, these two notions will have some approximation error, and here we'll omit them for simplicity. And in our setting, motivated by practicality, we also want the efficiency requirement, which means both parties should run in polynomial time. Correspondingly, this has the following effects on this problem. On the one hand, only server is not powerful enough to compute a QMA certificate. So we can't treat this problem as a complexity problems like QMA class. But on the other hand, malicious server is not powerful enough to break crypto assumptions. So we can use crypto tools to study this problem. We know that in the soundness notion, we only require no efficient server who makes the client accept. If the server model is unbounded, that means unconditional soundness or information theoretically soundness. But here we only require no efficient server. This is called computational soundness, which is our focus. Now let's give a review of existing works. There are many existing works, and this problem has a very long history. In the early stage, people have studied many weekend settings for this problem. And a very famous weekend setting is as follows. Let's assume the client has a small quantum device, which might be able to prepare a single qubit state or make some single qubit measurement. There are a lot of great results in this setting, and we already know in this setting, we can achieve unconditional soundness. However, one drawback of the protocol in this setting is the total client-side quantum computation scales at least linearly with the size of the circuit to be verified. And for some protocols shown here, the complexity might be quadratic or even cubic. Which means this kind of protocol seems hard to implement in practice at a scale. Because in terms of client-side quantum computations, if we consider the total number of gates, actually there's no decrease on the amount of computation that needs to be applied by the client compared to the original circuit, which is a big drawback. Another class of weekend setting is as follows. Let's assume there are two non-communicating servers. So the client could use the joint behavior of these two servers to test each other. And here we know, in this setting, we can construct a protocol where the client is completely classical, and we can achieve unconditional soundness. And the study of verification problem in this setting has led to many celebrating results, including the characterization of complexity class MIP star. But in terms of practicality, this class of protocols still seems hard to implement in practice at a scale. For example, that's because in the quantum network setting, how could we guarantee two servers that we are using does not communicate with each other? We could guarantee that by relativity. But if we want to apply these protocols on large-scale computations, it's still very hard to do that in practice. So what could we do? Relatively recently, people have figured out how to use cryptographic assumptions to solve this problem. In paper Mahadev 18, it also shows how to use a single quantum server and a complete classical client to solve this problem. And that protocol has cryptographic-based soundness. And this type of protocol seems more promising in terms of practicality. And let's wait for error-corrected quantum computers and see. The appearance of these protocols has led to great success in quantum cryptography. Here we use CVQC to stand for classical verification of quantum computations. And by default, we mean protocols with only a single quantum solver. Since the appearance of Mahadev 18, people have studied many quantum cryptographic protocols that build on either protocols or techniques of Mahadev 18. These include multiparty quantum computation, zero knowledge obfuscation, and so on, which could potentially lead to many future works. And all of them are very fundamental cryptographic primitives, and their classical analogs have been widely used in practice. It seems that everything's good, and we can build so many quantum crypto primitives based on Mahadev 18. But really, is this the end of the story? So let's see what will happen if we run Mahadev 18 in practice. Suppose you have a circuit C and an output O to be verified. You tell the remote quantum solver, I want to verify this validation result. Let's use Mahadev 18. So what should the solver do? Following the protocol, for a fixed security parameter, the solver needs to run a cubic size quantum computation. We'll see the size of the circuit to be verified. If you do this in practice, with high probability, the company will tell you, building quantum computers is really very hard. We don't want to run a cubic time protocol. For example, if the circuit size C is, for example, 10,000, and you take its cubic, it will be 1,000 billion. 10,000, a circuit with 10,000 gates is actually a very small circuit, but a circuit with 1,000 billion gates is a very big circuit, which means this will be a very big barrier for taking this protocol into practice. And these protocols is hard to implement in practice even for intermediate size problems. And this leads to a big problem. The cubic time complexity in Mahadev 18 is also inherited by all the protocols in this diagram. Everything here is in cubic time, which makes the practicality of all these protocols in doubt. And the cubic time complexity is dominated by the server-side quantum computations. Considering the preciousness of quantum computations, this might not be what we want. So here comes our results. In this work, we construct a new CVQC protocol, a classical verification quantum computation protocol, which runs in linear time. In more detail, it shows that quantum computation verification is possible with a completely classical client and a single quantum solver, which is the same setting as Mahadev 18. And the total time complexity is linear to the circuit set to be verified. And here the complexity is measured by the total time complexity, including both the client-side classical computation and server-side computation. And the assumption we used are the non-zero closure functions, or NTCF, within this paper, and the quantum random oracle model within this paper. Both assumptions are extensively used assumptions in quantum crypto. In the details for the time complexity, it could be written as poly kappa times c, where kappa is a security parameter. We note that in crypto protocols, since the soundness is only computational soundness, we need a security parameter kappa to control to describe how sound the protocol will be. Intuitively, if the security parameter is kappa, the protocol should be secure against adversaries that runs in time. For example, sub-exponential kappa or arbitrary polynomial in kappa. And here the polynomial is dominated by the complexity of the NDCF function, which can be constructed easily from the minimum error assumption. Which means in our protocol, there's no complicated complexity blowup hidden in this polynomial. So before we go to our protocols, let's first review the two assumptions that are used in this paper. The first is the NDCF function. This primitive is raised in this paper. Formally speaking, this function is a 2-to-1 function, which means two elements in the domain correspond to the same element in the range. It's a little bit like the function in the Simon's problem. And this function has a drop-down information. And forward evaluation of this function is easy, but the backward evaluation or the inversion is hard unless you use the drop-down. This function could be constructed for the linear with errors assumptions, which is the famous post-quantum assumptions in cryptography. And this assumption is used in many works that appeared this year. A typical evaluation protocol is as follows. The client could first sample an NDCF function together with its trap.td. Then the client could send out the function description to the server, but keep the trap secret. Then the server could evaluate the function in superposition and measure the output. This will collapse the overall state to a state in the form x0 plus x1 tensor y. And here, y is a random element in the range. X0 and x1 are two pre-images. Recall that this is a 2-to-1 function. Then the server could send y back to the client. And the client could use the trapdoor and function output y to invert the function and get x0 and x1. So the client could get both, but the server only holds the superposition of these two strings, which means it could only get one by mirroring it, but not get both. So this is one assumption. Another assumption that we will use is a quantum random oracle model. This model is raised in this paper as a quantum generalization of the classic random oracle model. In this model, there is a global oracle, which encodes a random mapping. All the parties can curate these oracles. And quantum means these parties can curate these oracles quantumly in superposition. For the same input, the oracle will output the same output with a random string. And for different inputs, the oracle will output different outputs, which are independently random strings. This is an ideal model for hash functions or symmetric encryption. We can design protocols in this model. And in practice, we instantiate the oracle with the hash functions or block cipher. This is called random walk methodology. We note that there do exist unintelligible constructions, like the constructions given in this paper. The security claim in this protocol, in this model, when we instantiate it, is ultimately heuristic. But on the other hand, these two models are extensively studied and widely accepted in cryptography, and they provide only known constructions of many cryptographic protocols. So returning to our protocol, we designed CVQC protocol in linear time, and we want to see whether we can build this protocol, also whether we can build these cryptographic primitives based on our protocol. Could we take these protocols, all these protocols down to linear time? And furthermore, could we take these protocols into practice? So starting from this point, I will discuss some technical details of our result. So before that, I wonder whether you have any questions. Any questions are welcome. I will stop here for some time and wait for some questions. So if you have any questions, please use the chat box. Also, do you know any negative results for information theoretically secure one server protocols? So I assume you mean classical kind one single server protocols that achieves IT security. I don't think there is any. I don't think there is any understanding for this problem. Actually, both on the positive part and negative part. For related problems like blind quantum computation, people have some negative evidences, but anyway, blind quantum computation is different from verification. So basically, we don't have any understanding for this problem. So this problem is actually the famous BQP versus QPIP problem. So sometimes people refer to BQP versus QPIP by, is it potentially possible? Yeah, you could say it's, but yeah, theoretically there is such a possibility. Possibly you could design a protocol. You could prove BQP is equal to QPIP with IT security, but we are far from it. What I can say is we are far from it. Thank you. So I will continue to the technical part. So in the third part, I will discuss the techniques that I use in our work. The way that blowup in sitting works. In paper Mahadev 18 and many other protocols, they usually take a Hamiltonian approach, which is roughly as follows. These protocols will transform the circuit validation problem to a Hamiltonian ground state estimation problem. And this transformation will lead to a Hamiltonian estimation problem whose estimation precision is required to be inverse quadratic in the circuit size. And that means to run this protocol, to estimate the ground state energy, the client need to collect quadratic number of samples. And each such collection requires linear time for the server to prepare the ground state. So it's qubit time in total. In this work, we take a completely different approach, which is to construct a remote state preparation protocol as an intermediate step. This allowed us to break this qubit complexity barrier. So what is the remote state preparation? We consider a similar setting as the verification problem before, but instead of verifying a circuit, let's consider state family F. Suppose the client wants to send out state file that is randomly sampled from F. And ideally, the outcome should be as follows. The client should have the description of the random state, and the server simply holds the random state, but does not have its full description. And we wonder whether there are any other way to do it than preparing and sending the state by myself. Because preparing and sending the state requires quantification and quantum channels, and we want to dequantize this part. So in the definition level, what we want is as follows. We want the client to interact with the server, and in the end, the joint state of the client and the server should be approximately the ideal state, where the client holds the description, the server holds the state. And additionally, so otherwise the client server should be called changing by the client. And additionally, we want the whole protocol to be classical channel, which means the client should be completely classical, and the instructions should also be classical. Here we call it classical channel following the conventions in related papers. So remote state preparation is not only important in our work, but also important in more general context. Because many quantum cryptographic protocols have a prepare and send structure as follows. The client will first prepare and send many gadgets. A gadget is a secret state randomly sampled from a simple state family F. The client prepares and sends this gadget to the server, and it keeps a description of these gadgets. Then both parties could do classical interactions, and the client could make use of these gadgets to ensure the server is doing something that he wants. So one drawback of this type of protocol is the client still needs to do many quantum computation and communication. And if we have a classical channel ISP protocol, we could replace the first step in this protocol, by classical channel ISP for this state family. And this will lead to a classical channel protocol for the whole quantum task, which achieves approximately the same functionality. And this means we got a compiler that compiles a quantum protocol to a classical channel protocol, which will be very useful. And returning to our problem of quantum computation verification, there are a lot of work that has a prepare and send structure. For example, in the FK12 paper, the authors gave a protocol whose gadget family F is a plus theta state union the standard basis state, which is a simple single qubit state family. The plus theta state is a plus state with additional phases. from 0 to 7. But one drawback of this protocol is the total gadget number required in the protocol scales quadratically with the circuit size, which is a blowup. But later in this paper, the KW17 paper, this quadratic blowup is removed. And the authors shows quantum computational verification is possible with linear number of gadgets from this state family. And later, in FKT18 paper, the authors simplify the state family and shows quantum computational verification is possible with linear number of plus theta gadgets. So what we aim to do is to construct a fast parallel classical channel remote state preparation protocol for this state family. So let's give a review of existing protocols for classical channel remote state preparation. People have already done a lot of work on this problem. And suppose we are aiming at preparing L gadgets in the form of plus theta. The paper GB19 and CKW19, the authors give protocols that are powerful enough to prepare this form of gadgets. But sadly, the time complexity is either estimated or estimated to be very large. Its scale is polynomial, but the exponent is about 50 or 100. And it also has a very big round complexity, which is approximately the same as the time complexity. And recently, the paper GMP22 and WC22, the authors give composed versions of the predecessor protocol. And the time complexity is still very large. And it's not clear whether, and these protocols aim at some non-trivial state families, but it's not clear whether they are powerful enough to prepare the plus theta state that we want. So based on the current advances of remote state preparation, it seems that remote state preparation is a problem that is even more difficult than CVQC. So here comes our results. We construct a linear time ISP protocol for plus theta states. In more detail, we give a new classical channel remote state preparation protocol for plus theta states such that we can use it to prepare L such states in parallel, and the time complexity scales linear in L. In more detail, at the end of the protocol, the client will hold theta 1 to theta L, where each theta is sampled randomly from 0 to 7. And correspondingly, the server will hold plus theta 1 to plus theta L. Otherwise, the client rejects. And additionally, our protocol runs in constant runs, which is a desirable property. And the assumption we use is NTCF function as Q room, which is the same as what we discussed before. So as a corollary, we can compose this protocol with the FKT18 protocol discussed just now to get a linear time CVQC protocol. Finally, let's give a simple overview of technical details of our construction. Let's first give a review of a seating approach. The seating approach for remote state preparation of plus theta typically goes as follows. This protocol will first use existing techniques based on mainly this paper, BCMVV18 paper, to achieve the following. the client will host a random theta from 0 to 7, and the ONI server will host plus theta, which achieves the ONI's mapping. And both parties will do this for each gadget independently. And starting from plus theta, the client will sample code and either do different tests to verify the server is really holding plus theta state, or do not do any test, or does not do any test, and simply use this state as output state. And because these tests are destroyed, and because the state will be destroyed by this test, so this random selection could be considered as a content truth technique. And the client and server will do this for each gadget. And the remaining state will be the state that we want, as long as the server could pass the test. So where is the blowup? There are two sources of blowup. First, the tests that we can design on these plus theta states turns out to be very inefficient. And second, protocols with this structure will suffer from an inherent individual testing barrier, which informally goes as follows. Suppose we want to use this protocol with this structure to construct L gadgets. And if we want a constant or the overall error of these L gadgets to be a constant, that means on average, each gadget could only have inverse L error. And since the probability of detecting errors is the square of norms, that implies for each gadget, for these tests, there's a lower bound or the inverse quadratic lower bound on the probability of detecting cheating behaviors with these tests. And that means even if we use this type of protocols to design remote preparation protocol, there's no hope to achieve linear time protocol. So what do we do? Our approach is as follows. And we will put the existing approach in the left-hand side for comparison. The first difference is different for existing approach. We will do the following in parallel. The second difference is we will first use some techniques to allow the ONI server to do something, but we will not allow the ONI server to prepare plus theta state directly. Instead, the ONI server will prepare an encoded ONI state in the following form. Here X0 and X1 are two long strings, which could be understood as the encryption keys of this state. And we can see if the client reveals X0 and X1 to the server directly, the server could decode the state and get plus theta state, where theta is equal to theta 1 minus theta 0. But we don't want to allow the server to decode directly. And the client will sample code starting from this point and either do some tests to catch the malicious server's behavior or reveal X0 and X1 to allow the server to decode opposite state. And furthermore, we bypass the barriers in the following way. Since our approach applies on each gadget in parallel, in the design of these new tests, we can test all the gadgets collectively instead of individually. And this means the total error of all these protocols is not the sum errors for each individual gadgets, which bypasses the individual testing barrier discussed just now. And since we work on the encoded only state instead of the plus theta state, this allows us to design various new tests that is not possible to do in the plus theta state. And furthermore, we make use of some techniques that originates from our previous work. Note that these two papers are all my previous works, and they provide some key insights that are useful in the current works. In summary, we design protocol. We design classical verification quantum computation protocol that runs in linear time. And along the way, we design parallel remote state preparation protocol for plus theta state that runs in linear time. And we expect applications of these results and techniques in different problems. And we also expect some potential practical impact of possibly improved versions of our protocols in the area of error-corrected quantum computation. Thank you very much. Any questions? You can hear me, right?
Can you hear me now?
Yeah, I could hear you. Okay, thank you.
Okay, I see. Yeah, so in your protocol, you have like linear dependence on circuit size, but you have polynomial dependence on the security parameter, right?
Yeah.
Yeah. And what is the size of the typical, what is the size of the security parameter for this verification task? The
security parameter just control the soundness of the protocol, and possibly in the usual crypto systems, take kappa to be 100 or 200 or 400 is usually sufficient. And that cost should exist in almost all the computationally secure cryptographic protocols, not just our protocol. It should appear almost everywhere.
Yeah, but I'm thinking that implementing trapdoor Clauffel function, is one of the bottlenecks of many of the this protocol, like self-testing or trapdoor, or proof of quantumness protocol or verification, like anything you take.
Yeah,
and you still have like this polynomial dependence on the security parameter. So I was wondering, how will that affect the feasibility of the approach?
So if you use the real OW assumptions, that will take the polynomial down to quasi-linear. But in terms of the practicality, it's certainly the overhead is certainly much bigger than what we can do in near term. But in the future, in the error-corrected quantum computer area, I think the blow-up should be comparable to the blow-up that the classical cryptography introduced in classical world. That's my intuition. It's not the construction from any real with error to trapdoor cryptographic functions is not that complicated. It's just it's not a complicated construction. It certainly introduced some overhead, but yeah, we need some estimate. We need to do some.
Why I'm saying this, because it could be possible that the circuit that you want to run is not very large. On the other hand, the implementation of the TCF, that might be the most costly part. So
yeah,
even if you bring your dependence from cubic to linear on the circuit, the cases where circuits are not that large, you know, like the dependence on the security parameter could be a big bottleneck. So a related question that I have is that the polynomial dependence on the security parameter that you have, is it same like as previous works, or do you have a different polynomial?
In terms of the security, in terms of polycappa term, I think it's comparable. It's in the same order. And for the constants, the given constant is a big notation. In the current security analysis, our protocol is much bigger, but I don't think the current analysis is tight in any meaningful sense. I just, when I do the security analysis, I don't care about the constant at all. So the current estimate is impractically big, but I believe that we could do something to optimize it. Oh, so I also want to say the Mahadev protocol also has a polycappa blowup. So the polycappa term is comparable, and the constants need to be improved in the future. Is it helpful? Is it helpful for you?
Yeah, thanks. Yeah. I mean, so I don't know if other people have questions they can ask, and I will ask later. Yeah, maybe I want to ask a follow-up, but yeah.
Hi. Okay, so thanks for the talk. Okay, so would it be possible to sort of summarize the main new techniques that you develop over previous works that help you bring down the time complexity from cubic to linear?
I think I developed a new framework that, so first I give up the Hamiltonian approach. If you do the Hamiltonian approach, I don't think there is a way or an easy way to bypass the cubic barrier. So I took the remote state preparation approach. And although existing work for remote state preparation are all very efficient, but I succeed to develop a linear time remote state preparation protocol. And for remote state preparation part, I also tried a new route that are different from many existing works. And in many existing works, there's also a barrier that affects the complexity of the remote state preparation, and which is the individual testing barrier that I discussed informally in the slide. And I bypass this barrier by introducing collective tests on all the gadgets, which means in our protocol, the tests is not applied independently or separately on each gadget. So this is a test that combine all the gadgets together and do a global tests on all the gadgets. And this will bypass the barriers.
I see. So it is the global tests that help you reduce the time complexity.
Yeah.
Okay, great. I mean, actually, one more thing that we sort of noticed that is it true that many papers coming in this area are, because we noticed that many papers coming in this area are like really long papers?
Yeah.
Okay. So is it because there's a lot of things to be done on top of the previous works, or what happens? I mean, like how is it that so many new things are done on top of previous works?
For my paper, I need to analyze each test. I need to design a lot of tests, and I need to analyze each test. And each test will possibly take more than 10 pages.
Oh.
So it's not just about the analysis. I need to explain the intuition. I need to define them, and I need to state the theorem, which will introduce a lot of notions. And I need to do the proof. And each test will take about 10 pages, and overall speaking, the paper might be about 100 pages. But I think actually in cryptography, many papers goes like this. In cryptography, it's very common to meet a paper that is longer than 50 pages. Also, it might be not that common to meet a paper with more than 100 pages.
I see. So many papers in this kind of the verification or blind computing, this kind of area, many papers are, you're saying, are already quite long, huh?
Yeah, right.
Okay. Okay, thank you.
I don't know if there are other questions.
Okay.
I have a very simple question.
Yeah.
I don't know whether it makes sense or not. So like you mentioned that there are two approaches, right? One is that one is based on the TCF and the noisy trapdoor closely function, and the second approach is the one based on quantum random oracle model. So, among
both assumption.
Sorry.
In this paper, I use both assumption.
Yeah. So I'm asking, like, in terms of resource cost, like when which of them are more require more resources?
Oh, so in terms of practical implementation, if you only consider one application of anti-self or random oracle, then certainly anti-self will spend much more resources because it's a public key encryption, and random oracle could be instantiated by a symmetric encryption. But on the other hand, anti-self will also allow you to do a lot of things, and random oracle on its own might not be that powerful. And if you want to, so you have to use some type of anti-self, and that will, and if you want, what I mean is if you want to remove the usage of anti-self and rely on some other techniques, that might lead to an even larger overhead than using anti-self. So I think for this problem, even if anti-self will cost will lead to a lot of overheads, it might be necessary.
So I mean, I was wondering because like recently there have been many attempts to design proof of quantumness protocol based on these techniques, and since like I mean and there was a talk at QIP also where they talked about depth efficient proof of quantumness, where they reduced the circuit requirement for implementing trapdoor Clophy function from log to constant. So like in 14 to 18 layers, they can implement, I mean, the bad part there was that, the width requirement that was too large. Right? And then, yeah, so it was a very wide circuit. And I think I noticed last week there was a paper by Mark Gendry, or I don't remember exactly, where they used this random oracle model, and they have also provided a proof of quantumness protocol in their paper. So I was thinking, what, because one can use Alexandru's compiler, the depth efficient compiler, and can definitely have a depth efficient implementation of trapdoor classic function at the cost of large width implementation. Or one could move into this Mark Gendry kind of implementation of QROM. And since, because after the some of the recent results which have questioned cross entropy benchmarking based proof of this quantum advantage, the sampling based advantage protocols, what remain to be, what possible hope in the near term is that one could try to do proof of quantumness either via this QROM, or using trapdoor classic functions. And I was wondering, since you looked at both of them in your paper and have intuition, which of these you think could be a more viable route to demonstrate quantum advantage, in near term?
I don't think this question is trivial to answer. We need to do research to really estimate both directions. This is a research topic. It's not something that.
So nobody has just compared QROM. You mentioned there have been different, I saw that there were separate papers, but people have been looking at it. But I think in your paper, though, even if you looked at it, you are saying that nobody has done a resource estimate and looked at which one can be better. I see.
Right. So certainly public key encryption should be more costly than symmetric key encryption. But if you can also consider the additional overhead, then no one really compares them. I don't think so. I don't think anyone has compared them.
I see. Yeah, thank you.
I think we can thank the speaker.
Thank you very much.
With a virtual applause.
Yeah, thank you.
Thank you very much, and
Thank you.
see you soon again.
See you.
Okay.
See you. Thank you.
Bye.
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 Thanks a lot.